Um, I have a slightly embarrassing confession to kick off this deep dive. A few years ago, I decided I didn't need a recipe to make waffles. I just sort of threw some stuff in a bowl.
But just throwing random things in a bowl.
Yeah, just winging it entirely. And when I pulled this thing out of the iron, I dropped it on the floor and, well, it bounced.
Oh, no. It actually bounced.
I mean, literally bounced like a rubber frisbee.
Yeah. You basically manufactured a stress ball instead of breakfast, which is a classic kitchen disaster.
Right, and I didn't know whether to eat it or play fetch with it, but it made me realize something. You know, a good waffle isn't an accident. It feels like there is some serious engineering going on there.
There absolutely is. It is a highly engineered system.
So today our mission is to break down the intersection of chemistry and engineering and thermodynamics to figure out how to take my rubber frisbee and engineer the ideal waffle for you.
We can definitely fix your frisbee problem because you probably look at batter and just see, well, goop. But in the technical literature, batter is actually called a reactive suspension.
A reactive suspension? That sounds like something from a chemistry lab.
It basically is.
Yeah.
You have starch granules and proteins and fat droplets just floating in water waiting for heat to trigger a chain reaction. If you mess up the ratios, you get the frisbee.
Okay, so flour is the main culprit here.
It is the skeleton. Flour provides the starch. And when that starch hits about 60 to 75 degrees Celsius, it undergoes gelatinization. The granules swell up with water and form a gel. That is what gives the waffle its structure.
So if I had way too much structure, I'm guessing I missed the fat. I always thought butter was just there for flavor.
Not just flavor, no. Think of fat as a waterproofing agent.
Waterproofing? Like it's wearing a raincoat or?
Exactly like a raincoat.
Mm.
Fat coats the flour particles and physically blocks water from getting to the gluten proteins. If water can't reach the gluten, you don't get that tough, chewy texture you experienced. It keeps the interior tender.
That makes a lot of sense. It is a balancing act. But what about the shape? I always assumed the grid pattern was just to hold a lot of syrup.
That is a very happy side effect. But the grid is pure structural engineering. It is analogous to architectural waffle slabs used in modern skyscrapers.
Wait, actual buildings use waffle patterns?
They do. A ribbed framework provides incredibly high stiffness and distributes the load, but it uses way less material mass than a solid slab. It is extremely efficient.
Getting a better result by being smarter about the structure. I love that concept.
It is all about optimizing the system.
And speaking of optimizing systems to get better results, that reminds me of our sponsor, Embersilk.
Oh, right.
If you are looking to uncover where AI agents could make the most impact for your business or even your personal life, you really need to check them out.
They are doing incredible work with AI training and automation, plus integration and software development.
Just go to embersilk.com for your AI needs.
Okay, so back to the kitchen. We have our reactive suspension and our grid structure. Now we apply heat. Is the waffle iron just acting as a hot pan? It is much more than a pan. You should think of the iron as a miniature heat exchanger and a controlled dehydration chamber. Its main job is managing steam dynamics.
And the steam is doing what exactly? Just escaping?
It is doing double duty.
Yeah.
First, it acts as a leavening agent, puffing up the gas cells to fill those grid pockets. But then it has to leave. As the steam escapes, it carries latent heat away to dry out the surface.
Right, because you can't get a crisp crust until that moisture is gone. So how do you know when it is actually done? I usually just guess and hope for the best.
You don't need to guess. You just use the audio test. Listen to this steam.
The audio test?
Yeah, at first you hear a really loud sizzle. That is intense phase change. Then it settles into a steady hiss of ongoing evaporation. When that hiss goes quiet, it means the surface is finally dehydrated.
Silence is the sound of crispness. I like that.
And that silence signals you have moved to the Maillard reaction. That is the browning from proteins and sugars reacting between 140 and 165 degrees Celsius.
Which is different from caramelization, right?
Yes, caramelization is just sugar breaking down at higher temps, usually over 160 degrees.
Now, I saw this fascinating chemistry hack in the research about pH levels. If I want better browning, do I just cook it longer?
You could, but you risk burning it. The smarter play is adding baking soda. It increases the alkalinity, which dramatically speeds up the Maillard reaction.
Wow, just a tiny adjustment changes everything.
Yeah, whereas an acidic ingredient like buttermilk will actually slow the browning down.
So the perfect waffle isn't just a food item, it is a highly specific material.
Material scientists literally call it a functionally graded material. You have a glassy, low-moisture exterior, protecting a plasticized, tender interior.
A functionally graded material. I am absolutely using that phrase next time I make breakfast. It is a beautiful, timed choreography of water loss and protein setting.
It really highlights human ingenuity. We take basic ingredients and apply physics to create something universally beloved. It shows we can engineer solutions to almost anything.
I couldn't agree more. It makes you wonder what other everyday foods are secretly advanced engineering marvels just waiting to be optimized by human curiosity.
There's always more to discover.
If you enjoyed this deep dive into the hidden science of breakfast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in, everyone.
Stay curious.